In this video, we look at the carbonyl bonding motif. That's a carbon-oxygen bonding motif, and it turns out to be very important in a number of different functional groups. The carbonyl bond is shown here, carbon-oxygen double bond. And of course, since carbon has 4 bonds, there are 2 other positions that can have functionalities on it. These can be hydrogen, they could be an alkyl group, or they could be a heteroatom. And that gives rise to the various functional groups, the aldehydes, the ketones, carboxylic acids, esters, and amides. We'll start off with the simplest systems, and that is the aldehydes and ketones. We talked about these earlier when we were looking at the oxidation of alcohols, and so we would see the formation of aldehydes and ketones. So aldehydes have the general formula RCHO, with the carbonyl group attached to a hydrogen and an alkyl group. The carbonyl carbon is always at the end of the molecule. It's always the terminal carbon that has been oxidized, and that's shown here. So we see a prototypical aldehyde. In a ketone, both of the single bonds on the carbonyl are attached to alkyl groups, and ketones have the general formula RCOR prime. The carbonyl group is found somewhere in the middle of the chain of carbon atoms. Aldehydes and ketones are very important. A lot of these you've come across. So aldehydes are known, they have very pleasant odors. There's a lot of very common tastes, from spices to fruits and flowers that are kind of manifest because of the aldehyde. There's an aldehyde molecule present. And actually in lecture I'll probably put up a slide listing a variety of different molecules that have familiar flavors. Ketones are very often good solvents. Here's an example shown here in slide B. Dimethyl ketone, but methyl ethyl, you may have used MEK, methyl ethyl ketone, as a solvent before. So these are important molecules. Now, the naming of these systems is relatively straightforward. For aldehydes, the systematic name simply takes the parent alkane E and replaces it with Al. And since the aldehyde is always at the terminal position, we don't need to specify its location. In example A here, we see a 5-carbon chain, and at the end of the carbon chain is an aldehyde functional group. So this would be pentanal. Ketones are named similarly, removing the parent alkane E and replacing it with the suffix ONE. But with ketones, we need to be more careful because we have to specify the location of the carbon-oxygen double bond. So here, for example, here's a 5-carbon chain, and so this would be 2-pentanone since the carbon is oxidized at the 2 position. If there's 4 or fewer, if it's 4 or 3 carbons, 4 or 3 carbon ketone, we don't need to specify the position. And the 2-carbon system, of course, is ethanal or acetaldehyde, so there's no ketone for that. There are cyclic ketones. Of course, they're not cyclic aldehydes. Those can only be on an aldehyde on a appendage off of a cyclic group. So if we take a cycloalkane ring and replace one of the carbons with a carbonyl group, we have a cyclic ketone. So for a cyclic ketone, we simply remove the E and add ONE. And shown here, we've got the 6-membered ring, which would be cyclohexane, and the corresponding ketone is cyclohexanone. The 5-carbon ring system, cyclopentane, if we put on a carbonyl here, we have cyclopentanone. And of course, anytime we have specified this, we've identified the carbonyl carbon as the 1 position on the cyclic ring. Now, aldehydes have many common names that you'll come across, and you should know these, at least the first few, because you will come across these. So typically, here we've got the C1 to C5 carbon systems, and the systematic prefix meth, eth, prop, butan, pent would give us methanal, ethanal, propanal, butanal, and pentanal. But the old common names simply take a different prefix and then add aldehyde to that. So for example, methanal, that one carbon aldehyde, CH2O, is more commonly known as formaldehyde, which you've probably heard. That's a preservative used for biological specimen preservation. Ethanal is more commonly known as acetaldehyde. Propanal is propienaldehyde. Butanal is butyraldehyde, and pentanal is valeraldehyde. Ketones similarly have a common naming system that's still in use. And the common naming system here is you simply identify the two alkyl groups in alphabetical order. If they're both the same, like in example A here, we put a di in front, so dimethylketone. But in B, we have two different groups, so we have a butyl group and a methyl group, so we'll call this butylmethylketone. Aldehydes and ketones, they have a dipole moment, and you would deduce this because carbon is bonded to oxygen. Oxygen has a pretty high electronegativity of 3.5, whereas carbon's 2.5. So the delta En is pretty large. So this is clearly a polar bond. And so it turns out that aldehydes and ketones have dipole-dipole interactions. So pure materials have that. So they tend to have higher boiling points than the corresponding alkanes or alkenes. So their melting points and boiling points are similar to one another, but they're higher than the corresponding alkanes. Now, from the perspective of solubility, of course, the aldehyde does not have an OH on it, but the oxygen can be a hydrogen bond acceptor to water. So both aldehydes and ketones, of course, they become less soluble as the hydrocarbon group size increases, but small aldehydes and ketones are soluble in water because the carbonyl group is acting as the hydrogen bond acceptor from water. And it turns out that the long-chain aldehydes and ketones are lower solubility in water. They're more than the corresponding alkane, of course, but they're lower solubility. They're not completely miscible. If we look at the reactions of aldehydes and ketones, of course, redox is the primary driver that we see. And so we've already discussed these, but we'll just reiterate this here. As we discussed in chapter 13, primary alcohols, they are oxidized to aldehydes. And then, of course, the aldehyde oxidizes to the corresponding carboxylic acid. And we'll discuss carboxylic acids later in this chapter. So aldehydes are oxidized to carboxylic acids. Aldehydes are reduced to alcohols. So there's two reaction pathways that are important for the aldehyde: oxidation to the carboxylic acid, reduction to the alcohol. Now, secondary alcohols, as we saw before, those undergo oxidation to produce a ketone. But ketones then are not further oxidized, at least with common oxidizing agents. Of course, they undergo combustion, which is an oxidation reaction, but in general, the ketones are less reactive, which is why they're good solvents. They do undergo reduction back to the corresponding secondary alcohol. Okay, so next up we're going to look at the carboxylic acid functional group. The carboxylic acid functional group is shown here in the shaded region of these two molecules. We have a carbon-oxygen double bond, which is what we're focusing on this chapter, but we don't have two alkyl groups. We have an alkyl group and a hydroxyl group. So we're singly bonded to the hydroxyl group. So this COOH or CO2H group is known as a carboxyl group. The general shape of the group you can imagine is, of course, it's planar around the carbonyl moiety. It's bent at the OH, and then there's rotation on the OH. So there's, the OH can act kind of like a small propeller. Here's some examples of carboxylic acids. You have tasted, smelled, and interacted with lots of carboxylic acids. You've got carboxylic acids in your body. They're all over the place. But here are three common ones. The first one in A is what's known as methanoic acid. Using kind of a similar naming scheme to the aldehydes, it's sometimes called formic acid. Coming from the word for ant, actually, sometimes you'll actually smell this. If you smell ants, crushed ants, you'll actually smell formaldehyde. And then next, you can see the picture of pickles. This is ethanoic acid or acetic acid. It's what is the primary component of vinegar, right? So pure vinegar is acetic acid or ethanoic acid. And you guys, I'm sure, have tasted that and handled that before. And the last one is pentanoic acid, which is also called valeric acid, and you can see where the name comes from. It's present in the valerian plant. Now, there are other common examples of acids, and I'm going to just throw one out right here while we're talking about these, and it's called butyric acid. And butyric acid, or butanoic acid, you can guess has 4 carbons on it. And that's actually what causes vomit to kind of have the vomit smell and taste, that sour taste. Acids tend to be sour. And I have a colleague who's from Britain. He and I, we do research together. And he does not like American chocolate. He only likes British chocolate. Because it turns out when American chocolate is made, the milk is actually processed a little bit further, such that a little bit of butyric acid is produced. And as Americans, you get used to eating chocolate from, Hershey's chocolate in Pennsylvania, and it has a little bit of, it actually has a little tiny bit of that taste, that kind of sour acid taste in it. It's not overwhelming, of course, but it's there. But for those who've not had that kind of chocolate, and in particular in Britain they don't do this, my colleague from Britain says that American chocolate tastes like vomit. So next up, let's name carboxylic acids. It's actually quite similar to aldehydes because the carboxylic acid is always at the end of the chain. So the systematic name of a carboxylic acid takes the E at the end of the parent alkane and replaces it with OIC acid. And alkyl branches and all the other substituents we treat just as we've treated up to this point. And there are some common names, and we've kind of mentioned a few of these already. So down here on A, you can see that this is a 5-carbon chain. That would be pentane. And so the corresponding carboxylic acid is pentanoic acid. And next up, we have a 4-carbon chain with a methyl group on the side at position 3. So the 4-carbon chain tells us it's butanoic acid. And then we've got a methyl at the 3 position, so we would call this 3-methyl butanoic acid. There's a older naming system, and it's one that's actually important, particularly when we talk about biological systems. And it's a Greek letter naming system for identifying positions on carboxylic acids. So look at the figure first. You can see you've got a 6-membered carbon chain. So that's a hexane chain. This would then become hexanoic acid. But one of the naming sequences that's commonly used is a Greek letter symbol for each of the carbons after the first carbon. So you have your carbonyl group, and then the next carbon attached to it is alpha, the next one's beta, the next one's gamma, then delta, then epsilon, and so forth. So turns out that there are things called alpha hydroxy acids, which you may have come across before, or maybe not. I mean, you may have seen it on a commercial, and that has an OH, and you can guess where the OH position is. It's at the carbon 2 position. There are also aromatic carboxylic acids. But in this case, of course, you can't oxidize the ring carbon to get there, like you would in cyclic aldehyde, for example. But you can have a carbonyl group attached to this, or a carboxyl group attached to this. So the simplest aromatic carboxylic acid is benzoic acid. So it's kind of similar to phenol in a sense. Benzoic acid is used as the parent name for the other aromatic carboxylic acids. And that's, of course, the 1 position. And so in B here, you can see you've got your benzoic acid, but you have a methyl group on it, and it's in the 4 position. So we could call this either 4-methylbenzoic acid or paramethylbenzoic acid. Now, the carboxylic acids, as you can imagine, have plenty of hydrogen bonding. They've got 2 polar groups, the carbonyl group, that's a hydrogen bond acceptor, and a hydroxyl group, which is a hydrogen bond donor and hydrogen bond acceptor. So carboxylic acids exhibit very strong intermolecular forces because of this, and they tend to have high melting points and boiling points. Much higher than, a good bit higher than the corresponding alcohols, and definitely much higher than the corresponding alkanes. So carboxylic acids that are larger actually are solids at room temperature because of these strong forces. Carboxylic acids, of course, since they've got an acid moiety on them, they are highly water soluble. The small ones are completely miscible. So the C1 to C4 carboxylic acids are completely miscible, and then the ones that are C5 and higher are still quite soluble, but they tend to become less and less soluble as the R group becomes bigger. Looking at the reactions of these systems, in water, as you can imagine, the carboxylic acid group is an acid. It's a weak acid, so it tends to donate protons to water, giving H3O+, and then its conjugate base, RCOO-, which we call a carboxylate. The formulas of acids may be written with hydrogen at the beginning to indicate the first hydrogen dissociates, kind of trying to be similar to mineral acids. But generally for organic chemistry, we write RCOOH, and it's the final hydrogen that is the dissociating species. The conjugate base, like we said, is called the carboxylate ion. Carboxylate ions are named just the same way we would name carboxylic acids. We replace the ending with ATE in this case. So the IC acid becomes 8, just like, for example, nitric acid becomes nitrate, if you remember that from back in basic chemistry. So when methanoic acid reacts, like if it was up above, the conjugate base is methanoate. carboxylic acids, they're weak acids, but they react with strong bases and they form salts. So here's an example. We have methanoic acid or formic acid reacts with sodium hydroxide to form water and sodium methanoate. So here are the names and kind of connecting names with structures for the acid and its conjugate base carboxylate. Methanoic acid, which we also know as formic acid, has a formula HCO2H or HCOOH, and its carboxylate, its conjugate base, is named methanoate anion, but it's also called formate ion. You'll see a formate, and that structure is HCO2 minus or HCOO minus. Ethanoic acid, which is more commonly called acetic acid, CH3COOH. If this loses a proton, we have ethanoate ion or the acetate ion, and that gives us CH3CO2 minus. Propanoic acid is commonly called propionic acid, shown here with its formula, and its conjugate base is propanoate ion. The common name propionate ion is probably not quite so common with that. And then finally, our butanoic acid, the stinky acid, butyric acid. Its conjugate base is butanoate or butyrate. So there are other cases where carboxylic acids have important applications. So here's an example. Benzoic acid can react with potassium hydroxide to give potassium benzoate and water. And if you remove the water, you end up with the salt. It's a crystalline salt, potassium benzoate. And you will recognize that because that's used in a lot of beverages, particularly sweetened beverages. And it's there to act as a preservative. If any bacteria get in, of course, the potassium benzoate get inside the cell, they lower the pH, and that shuts off the pathway, allowing the sugar to be oxidized. And so it keeps the quality of the beverage for a much longer period of time. There are polyprotic carboxylic acids. So these are molecules that have a carboxylic acid at multiple ends. So in figure A, we've got a simple one. This is a 2-carbon chain, so it's like acetic acid, but instead of being acetic acid, it's got both carbons have been oxidized to a carboxylic acid. So you've got 2 CO2H's on one molecule, one small molecule. And this is called commonly called oxalic acid, and it's found in a lot of vegetables, also found in cocoa. It turns out that it's very prevalent in spinach. And we don't have time here to do it, but if you want to discuss this in class, we can go over the chemistry of oxalic acid and the conjugate base oxalate, which tends to bind to calcium. And if you have a calcium deficiency in your body, it's not good to eat spinach because that can lower your available calcium. Citric acid is another one. You can see that this is a tricarboxylic acid. And citric acid is what gives the particular sour citrus flavor to many citrus fruits. That's the end of the first part of chapter 14. The next video will complete chapter 14.